Molarity is the concentration that chemists use a lot, because chemists, as you may have noticed, care about moles, not the little furry animals. But we care about moles of this and moles of that, because when particles react, they do so in terms of numbers of particles. And the mole is our chemist's dozen that tells us about the number of particles. So molarity, if you transpose the R and the L, you get morality, but that's not what we're talking about. Molarity, abbreviated capital M, it's the moles of solute divided by the liters of solution. Mass percent was grams of solute per gram of solution times 100, right? So this is a similar idea. We've got the solute over the solution, but now the units are very specific. We need moles and liters. And again, this is moles of solution, not solvent. When we make a solution of a specified molarity, we usually put the solute in the flask and then add water and mix it and then add water again until it gets to the right volume. So we don't actually ever even measure the volume of the solvent. That doesn't really matter at all. We want the volume of the solution. So here is your book's illustration on how to make a solution. I would do it slightly differently, actually. I would start out with this flask partially full of solvent. I'd put the solvent in there first. Then you're going to add, for this is how to prepare a 1 molar solution. That does not mean that there's 1 tooth in the solution. That's how we would read the capital M. So this would be 1 mole per liter. So we're going to have 1 mole of sodium chloride, which is 58.44 grams. We're going to put that in here. And then we're going to add water. We're going to add water until it gets up about here, and we're going to mix it and make sure that everything dissolves. Then we're going to finish adding water until it gets to the mark. This particular style of flask is called a volumetric flask. And it is more precise, much more precise than like a beaker. And it's a lot more convenient to use than, say, a graduated cylinder. You could make a solution in a graduated cylinder, but it's pretty hard to mix because it doesn't have a lid. And it's tall and skinny, and you can't just swirl it or something. The reason this has this tall, skinny neck is the same reason that graduated cylinders are tall and thin. Because then if you have a small difference in volume, it's going to be a big difference in the height of the water in this narrow part of the flask. And so you can get a more accurate measurement of your volume. So you fill it until the bottom of the meniscus is at the mark here, and you know you have 1 liter. Then you would put a stopper on this and hold the stopper with your thumb, and then you have to turn it upside down, wait for all the air to go up, and then invert it again. And you need to do that about 20 times to get it to completely mix. Because once it's got water all the way up in the neck, you can't just shake it and get it to mix around. It's kind of stuck. That's why you want to do all your shaking and dissolving before you fill it up into the narrow part of the neck. So let's do an example of calculating molarity. Calculate the molarity of a solution made by putting 55.8 grams of sodium nitrate into a beaker and diluting to a volume of 2.50 liters. So the first words here, calculate the molarity. Molarity equals what? Moles of solute over liters of solution. The abbreviation for molarity is capital M. Why did I underline my M? Well, I'll show you. Is that a lowercase m or a capital M? That's a capital M. You can't tell, can you? And we sometimes get kind of sloppy even in the relative sizes of our lowercase and capitals. So if I mean it to be capital, I'm going to underline it, and that means that's a capital M, even if I made it a little curvy or too small or something. So you'll see me underlining M's, and that's why. It's force of habit, I can't stop. We need moles of solute and liters of solution. Do they give us either of those? What's this guy? That's volume of the whole solution, right? We put this solid in a beaker, they added water, diluted it. This is the volume. Okay, we try to trick you with the percent calculations because we can. The molarity ones, we really can't. So you don't have to be as alert for tricks on these. So the liters of solution is 2.50. What are the moles of solute? Did they just hand that to us on a platter? No, they gave us a mass. 55.8 grams of sodium nitrate. Can we figure out how many moles are in there? Sure we can. We do that all the time. We need the molar mass, right? Periodic table. 1 sodium, 22.99. 1 nitrogen, 14.01. 3 oxygens, 16.00. $85. My calculator says 85. That's like when you go to the grocery store and it comes out to be $100 even. Like you're like, what? Numbers don't usually come out even like that. How many significant figures should that number have? 4. Because we're not, our final answer will have 3. But down here, we're just calculating the molar mass. All of these have 4. How do we make this have 4? 0.00. Because sometimes what happens is you'll see that 85 and you write that down and then you put it in the rest of your equation, then you end up rounding things to 2 significant figures because you overlooked something. So you want to avoid that. So here, grams, we want to put grams on the bottom and we want moles on the top because we need to have the moles. When we calculate a molar mass like this, it's this many grams is equal to 1 mole. So we've got 1 mole and 85.00 grams. 55.8 divided by 85. So it says 656.47059. Technically, if we're rounding off, that's going to have, started to write the wrong unit. It's going to have 3 sig figs. But let's just carry a couple extras. I'm going to underline that. It's only got 3. Always a good idea to carry a few extra digits to avoid rounding errors. So then up here, we've got 0.65647 moles. And sometimes you don't even have to even really think about carrying extra digits. I still have that number in my calculator. And to do this calculation, I'm going to take that number and divide by 2.5. So I'm not going to type that in again. It's already there with all of its extra digits. Divide by 2.5. And I get, now we should round it, I get 0.263. 0.263. Yeah, that was, okay. 0.263. The units are moles per liter. That's acceptable, or 0.263 capital M. Questions? A lot of times they will give you mass. We weigh things out in grams, and then we convert to moles. The percent concentration made a good conversion factor, and the molar concentration also makes a good conversion factor. So let's look at this one. Determine how many grams of sucrose are contained in 1.95 liters of 0.781 molar sucrose solution. So what's jumping out at me is how many grams of sucrose. That's what I'm trying to find. And then I've got two numbers that are given. I've got 1.95 liters, and I've got 0.781 capital M. Now, you look at those two units and you're like, I can't do anything with that, right? L's and M's, What does the capital M mean? Moles per liter. Moles per liter. M for moles. Okay. I just taught you about that. It's okay. This is the same as 0.781 moles per liter. They are almost always going to give it to you as capital M. That is so much easier to put into the computer, right? You're typing it along, capital M. Occasionally, they might do something like with a slash, where it's still on one line, moles per liter like that. They might do that. This still is not a good way to look at it when you're writing stuff down. You're writing with your hand, okay? You're handwriting this. You can make fractions with no big particular effort. Write it down as a vertical fraction, because then you see very clearly that it is a fraction. Moles and liters. And that looks like a conversion factor to me. Moles per liter. When you write it like this, you lose its fractionness. It doesn't look like a fraction. When you write it like this, it looks like something very strange. Like two mountains or something, I don't know. So this is conversion factor. This other number is probably the thing we have to start with. So it's always helpful to write out a path. We're starting with liters. That molarity allows us to convert from liters to what? To moles. And our question asks for grams. Can we go from moles to grams? Yep, we can. So we're going to take this volume. We're going to put in a conversion factor here with moles on the top and liters on the bottom. And then next, we're going to have grams on the top and moles on the bottom. There's no formula to memorize. It's dimensional analysis. The units. Just look at the units. So moles per liter, that's our molarity. When you write the vertical line all the way under the number, that helps you to remember that this number is in the numerator. It's on the top of the fraction along with moles. And the liter is on the other side. So this is 0.781. And sucrose, we already did. I think this is 342.2, was it 69 or 96? Anybody have that written down? Or we didn't do that one yet. I'm jumping ahead. I did it this morning. We need the molar mass of sucrose. We're going to use it again, so we'll have to remember it. So sucrose, 12 carbons. Each carbon is 12.01. 22 hydrogens. Yes, that's a lot of hydrogens. It's okay. That's what it is. And 11 oxygens. Anybody have that number? 342.296. Thank you. Grams in 1 mole. So that goes up here, 342.296. Now really that only has 4 sig figs, but we'll just let that's a 9. We'll let the 9 and the 6 come along. So now we have 1.95 times 0.781 times 342.296. Except I typed it in wrong. 342.296. Okay, start over. That one was wrong. That's wrong too. I'm batting 1,000 here. 1.95 times 0.781 times 342.296. Oh, actually my second time was correct. 521, and that should have 3 sig figs. We've got 3 significant figures on this number and 3 on that number and 4 over here. So 521 grams of sucrose. Questions? It really helps when you're doing problems like this if you put units on every single number, even if it gets tedious. Write the units. Use plenty of space on your paper and write as neatly as you reasonably can so that you can actually see and understand what you wrote down. It really helps. So when we do something like sucrose, which is a molecule, we report the concentration. The concentration is actually that many moles of molecules per liter of solution. Oops. When we have an ionic solute, the molar concentration reflects the concentration of the solute before it's dissolved. So a 1 molar calcium chloride solution has 1 mole of calcium chloride. But when we dissolve that in water, the calcium ions and the chloride ions separate. So we've talked about how that works. The calcium chloride. You put that in water and it's going to separate into its ions as it dissolves. So from 1 mole of calcium chloride, we're going to get 1 mole of calcium ions and 2 moles of chloride ions because it comes apart. Just like if you had a dozen tricycles and you took them apart. A dozen tricycles would give you how many wheels? 3 dozen, right? And how many seats would you get? 1 dozen. Because from each tricycle you get 1 seat and you get 3 wheels. And so that's what we're doing here. We're just looking at the formula. In one of these units, there's 2 chlorines and 1 calcium. So if we had 1 mole per liter of calcium chloride, we'd have 1 mole per liter of calcium and 2 moles per liter of chloride. So the concentration of the individual ions can be approximated. We can't know exactly. In Chem 2, you learn a lot more about that. For now, we'll settle with approximate. And this whole ion concentration thing is, at this level, a minor point. So let's determine the molar concentrations of calcium and chloride in a 0.75 molar calcium chloride solution. Well, 0.75, what does that capital M mean? Moles per liter. Moles per liter. Moles of what? Moles of water? Moles of sucrose? Calcium chloride. CaCl2 per liter of solution. Now they're asking us what the mole per liter concentration of calcium ions is. So we would have to multiply by moles of calcium ions and we would divide by moles of calcium chloride. We did some calculations like this a long time ago. How many moles of calcium are in each mole of calcium chloride? 1. There's 1 mole of calcium per 1 mole of calcium chloride. So we end up with 0.75 molar calcium ions. You might say, well, that's dumb. Did we really have to do that? No, we didn't really have to. But it illustrates how you do the process. Let's do the same process for the chloride. 0.75 moles of calcium chloride per liter. Now we want to find out how many moles of chloride ions are in that same liter. So we'll multiply by moles of chloride, divide by moles of calcium chloride. How many moles of chloride per mole of calcium chloride? 2. Where did that number come from? The subscript in the formula. We don't have to look up anything. We're just looking at the formula here. There's 1 calcium and 2 chlorines. So there's 2 chlorines in each 1 mole of this, 2 moles of chlorine. And so the concentration of chloride will be twice as much as the calcium. Most of the time we don't look at concentrations of ions, but occasionally. Any questions?